This brief tutorial will show how easy it is to obtain buckling factors in ETABS. The buckling factor determines the magnitude of the load required to cause buckling of the structure. For this tutorial, we have created a slender 20-story building, only 48 feet square in plan. This shape was chosen as slender structures are more susceptible to buckling. This building was previously analyzed for dead load. Note that this includes self-weight, live load, which was 50 pounds per square foot applied to the floors, and wind loads based on ASCE 7-10. After the analysis, the design was run and satisfactory frame members were selected from auto-select lists. The key to obtaining the buckling factor is the creation of a buckling load case. To the previously defined dead, live, and wind load cases, we will add a new case, which we will call buckling. This load case will have, obviously enough, a type of buckling. For this first case, we will use the preset P delta setting of none. This means that no P delta will be used in the buckling analysis. Since P delta alters the stiffness of the structure and thus affects the determination of the buckling modes, we would typically specify that P delta be used, and we will come back to this later. For the applied loads, in the buckling analysis, we will use a combination of 1 times dead plus 1 times the live load. It is these loads that, when multiplied by the buckling factor, provide the buckling load. We will leave the number of buckling modes set to 6 and the convergence tolerance as is. Calculating the buckling modes is an iterative process, and the tolerance determines how numerically close iterations need to be to assume that convergence of the buckling factors has occurred. We can now run the analysis to include the buckling load case. With the analysis complete, we can display the buckling factors for each buckling mode. This can be done through the Display Show Tables command or via the Model Explorer. Under Analysis, we expand Results and then Structure Results and right-click on the Buckling Factors option to display. The buckling factors for each buckling mode are displayed. Note that the first mode of buckling will occur if we increased our applied loads by a factor of 2.142. Remember this number, as we will come back to it shortly. We will also expand load cases and display the load cases buckling option. This confirms our buckling case data. Closing the tables, and with the 3D view active, we will view the buckling modes. Selecting the buckling case, the step number represents the 6 buckling modes that we requested. With the first buckling mode plotted, note that the buckling factor is also displayed. Using the VCR buttons, we can step through the other 5 buckling modes. We can also display the relative forces in the members for each buckling mode. Selecting the first buckling mode and the axial force component, we see that the deformation in the first buckling mode is primarily isolated to the first story. As we go to the higher modes, we see that more stories are involved in the buckling. Next, we will unlock the model. We are now going to modify the buckling load case to use P delta. Remember that our initial buckling analysis did not have any P delta, and we said that it is important to include P delta when calculating the incremental buckling load. Selecting the buckling case and clicking the Modify Show button, we will alter the case to use P delta. Clicking the Modify Show button, we will use the iterative option based on loads, and we will use a combination of 1 times the dead load, which is self-weight of the structure, and 0.25 times the live load. This is the only change we will make. Rerunning the analysis, we can now redisplay the buckling factors to see how including P delta affected the results. Note that the first mode buckling factor is 1.434. This is considerably less than the factor obtained without P delta, which was 2.142. This is as expected due to the fact that P delta alters the stiffness matrix. Again, we can view the buckling modes. And view the relative forces for the buckling modes. Again, we see that deformation in buckling mode 1 is primarily isolated in the first story. As a last step, we will increase the applied loads by the buckling factor just calculated. Assuming that there is a linear relationship between the applied loads and the buckling factor, this should result in a new buckling factor of 1 for the first buckling mode. Unlocking the model, and returning to the buckling load case. We will apply a scale factor of 1.434 to each of the load patterns. Now when we display the buckling factors, we do indeed get a factor of 1 for the first mode, proving that as you increase the applied load, the buckling factor will decrease in a linear relationship. This concludes this tutorial on buckling factors.